Hello! In this video, we are going to prove the following theorem. Let S be a subset of real numbers. Then S is bounded if and only if there exists a positive real number m, such that for all elements x and S, the absolute value of x is less than or equal to m. Now before we get into the proof, let's get some context. To start, we're going to say that given any subset of real numbers S and a real number u, we say that u is an upper bound of S if, for all elements x in S, x is less than or equal to u. Similarly, we're going to say that given any subset of real numbers S and real number w, we say that w is a lower bound of S if, for every element x in S, x is greater than or equal to w. And finally, we say that given any subset of real numbers S, S is bounded if S has an upper bound and a lower bound. Now, in proving this theorem, we are going to use the following preliminary result. For all real numbers A and C, the absolute value of A is less than or equal to C if and only if the negative C is less than or equal to A is less than or equal to C. Okay, so now let's get into proving this theorem. To start out, let's give ourselves a subset of real numbers S. And from here, we want to prove that this is true if and only if this is true. And we're trying to prove a statement containing if and only if. So what we're going to do is we're going to prove if this is true, then this is true. And then we're going to prove if this is true, then this is true. Let's start out by proving if this is true, then this is true. And to do that, suppose S is bounded. Well, since S is bounded, we know that this means S has both an upper bound and a lower bound. And we'll say U is an upper bound of S and W is a lower bound of S. Now our goal is to prove that there exists a real number m greater than 0, such that m satisfies this condition. And we're going to define our number m to be the supremum of 1, absolute value of u, and absolute value of w. And we're going to show that our choice of m satisfies both of these properties. Well, to see that m is greater than 0, we know that since m is the supremum of this set, this means that m is greater than or equal to every element of this set. So in particular, m is greater than or equal to 1. And we know that 1 is greater than 0. So this tells us that m is greater than 0. So we see that our choice of m satisfies this condition. Now we want to show that our choice of m satisfies this condition. And we're trying to prove a statement about every element in S, so give me an arbitrary element of S. I'll call it x. And from here, our goal is to show that the absolute value of x is less than or equal to n. And to do so, we consider two cases. Either x is greater than or equal to 0, or x is less than 0. And in either case, we're going to show that the absolute value of x is less than or equal to n. Let's start with case 1, where x is greater than or equal to 0. Well, since x is greater than or equal to 0, we know that the absolute value of x is equal to x. And also, since u is an upper bound of S, we know by definition that means that every element of S is less than or equal to u. So in particular, since x is an element of S, x must be less than or equal to u. But since x is less than or equal to u, and x is greater than or equal to 0, we say that u is greater than or equal to 0. And because u is greater than or equal to 0, we must have that the absolute value of u is equal to u. And then we know that m is greater than or equal to every element of this set. So in particular, m is greater than or equal to u. And so as we can see here, this tells us that the absolute value of x is less than or equal to m. And that's exactly what we wanted to show. So this completes case 1. Now let's move on to case 2, where x is less than 0. Now, since x is less than 0, the absolute value of x is equal to negative x. But then, since w is a lower bound of s, we know that by definition, this means that every element of s is greater than or equal to w. So in particular, since x is an element of s, x is greater than or equal to w. But if we take this inequality and multiply -1 on both sides, we get that the negative of x is less than or equal to the negative of w. And also, since x is less than 0, we see that w is less than 0, which means the absolute value of w is equal to the negative of w. And again, m is greater than or equal to every element of this set, so in particular, m is greater than or equal to the absolute value of w. So we see that the absolute value of x is less than or equal to m. Now, putting this together, we have shown that there exists a real number m greater than 0, such that for all x and s, absolute value of x is less than or equal to m. Namely, our choice of m was this, right? We showed that our choice of m is greater than 0, so we satisfy this condition, and we also showed that our choice of m satisfies this condition, right? And the way we did that was we gave ourselves an arbitrary element in s, and showed that x satisfies this condition, right? So since x was arbitrary, this means for all elements x and s, the absolute value of x is less than or equal to m. And that's it. We have proven if this is true, then this is true. Now we're going to prove if this is true, then this is true. And to do so, suppose this is true. And our goal is to show that s is bounded, which means we want to show that s has both an upper bound and a lower bound. Well, we claim that m is an upper bound of s and the negative of m is a lower bound of s. And to see that, what we're going to do is we're going to show for all x and s, x is less than or equal to m, and for all x and s, x is greater than or equal to negative m. So let's give ourselves an arbitrary element of s. Call it x. Well, since this is true for every element in s, it must be true for x. Therefore, the absolute value of x is less than or equal to n. But then, we can apply this fact to obtain that the negative of m is less than or equal to x is less than or equal to n. So now, let's put this together. We started with an arbitrary element x and s, and showed that x is less than or equal to n. Therefore, for all x and s, x is less than or equal to n. And that's precisely what it means for m to be an upper bound of s. And similarly, we started with an arbitrary element x and s, and showed that x is greater than or equal to the negative of m. Since x was arbitrary, this means that for all x and s, x is greater than or equal to negative m. And that is precisely what it means for the negative of m to be a lower bound of s. So we see that s has an upper bound and a lower bound. Therefore, by definition, s is bounded. So we have shown if this is true, then this is true. And we've proven both directions of the if and only if, which means we have proven this entire statement. So this completes the proof. And so yeah, that's pretty much it for this video.